Let's consider a problem dealing with instantaneous values. That means we're going to use our set of motion equations. So our situation is that we have a boat taxiing in a no-wake zone at 8 miles per hour. Entering open water, it accelerates to 45 miles an hour in 3.7 seconds. First thing you need to do when you're dealing with instantaneous values and with any problem is to identify what you know, especially by symbol. So if we consider, we know, 8 miles per hour. That's how fast the boat is traveling in the beginning. So that would be VI. VI 8 miles per hour. Entering open water, it accelerates to 45 miles per hour. Another number in miles per hour, that's another speed or velocity. That would be the final velocity, 45 miles per hour. In other words, that is the velocity at the end of the acceleration. Now, we also know that it took 3.7 seconds to be able to do that acceleration. In part A, we want to calculate the acceleration of the boat. Now, notice our units don't agree. We're in miles per hour and we're in seconds. So I'm going to convert our mile per hour values into meters per second. 1 mile we know is 1,609 meters. Hours are on the bottom, so hours go on the top of our fraction. 60 minutes and 60 seconds, so that's 3,600 seconds. So then 8 miles per hour converts over into 3.58 meters per second. If we do the same conversions across our 45 miles per hour, we will get 20.11 meters per second. Now we're ready to select a motion equation and plug in values. So to be able to calculate the acceleration, I need one motion equation that has these 4 variables in it. Well, the first equation has all 4 of those variables. So I'm going to write the equation out. VF is equal to VI plus A delta T, and then plug in our values. So VF gets replaced by 20.11 meters per second. VI gets replaced by 3.58 meters per second. The acceleration is our unknown, so it stays as A, and our time period is 3.7 seconds. Now we want to solve this equation down for A. So what I'm going to do is subtract the 3.58 from both sides, and then after doing that, I'm going to divide both sides by 3.7. So then doing that, we get an acceleration of positive 4.47 meters per second squared. Again, positive and negative represent directions, and so the positive would indicate in this forward direction. So 4.47 meters per second squared forward. Part B. Calculate the displacement of the boat during this acceleration. Well, displacement symbol is delta x. So now we know VI, VF, delta x, or delta t, and we want to find delta x. So that gives us enough to be able to use this second motion equation. You could also use the acceleration you calculated in part A and use one of the other equations. And as long as you do the algebra correctly, you'll get the same value. So then the second equation, delta x equals 1/2 times the quantity VF plus VI times delta t. So delta x equals 1/2. VF gets replaced by 20.11 meters per second. VI gets replaced by 3.58 meters per second. And our time period gets replaced by 3.7 seconds. So then we're going to combine our 20.11 and 3.58, multiply that by 1/2, and that number that we get multiplied by 3.7 seconds. And so we're going to get a delta x value of 43.48 meters, again in that forward direction. So while the boat was accelerating, it traveled 43.48 meters per second forward. So when you're using the motion equations, list out what you're given. Really important to identify it by symbol. Do any necessary conversions, and then select the equation that has the quantities in that you need and plug your values in. Ponder physics.